Hello, everyone, and welcome to our first CBE lesson video of the semester. What is process engineering? Main idea is process engineering is about transforming raw material and energy into useful products for society. Process engineers work in a variety of industries, from food products and biofuel to biopharmaceutical processing to crude oil and natural gas engineering. Like you see in the bottom and right-hand pictures, process engineers work with devices which are called process units. Most process units involve pipes which transport material and tanks which either combine, separate, or perform any other physical process on the material. This is a bioreactor. Bioreactors are vessels which perform biological processes, such as the fermentation of alcohol. There are a lot of different things going on in this diagram, but process engineers use one very fundamental equation in order to understand the amount of material passing into and out of a system like this one. That equation is called the general balance equation. We say that the input plus the amount of material generated minus the output minus the amount that's consumed equals the total amount of material which accumulates inside the tank. For steady state processes, we say that there is no accumulation inside of our system. Next, Jocelyn is going to provide you a real-world example of how we would use the general balance equation. Then, Kofi is going to provide you a quintessential example of how the material balance is used in chemical engineering.
Hi everyone, so we're going to use the CBE concepts to look at a real-life example about a city and population. So this example says, each year 50,000 people move into a city, 75,000 people move out, 22,000 people are born, and 19,000 die. Write a balance on the population of the city. How is the population changing over time? So we can take our classic CBE equation, which is input plus generation minus output minus consumption equals accumulation. So in the problem, it says that 50,000 people move into a city. So 50,000 people can be attributed to the input because that is what is put in at first. Then it says that 75,000 people move out. So that can be attributed to the output. If you think about it, if this was the town, it says if 50,000 people are moving in and 75,000 people are moving out. And then it also says that 22,000 people are born. So 22,000 people can be the generation because they weren't really moved in or out of the town, but created within the town. And similarly, 19,000 people die. So that can be attributed to the consumption. Once we have all of our variables defined, we can plug them into this main equation. So overall, you get, if you plug everything in, you get that 50,000 plus 22,000 minus 75,000 minus 19,000 equals negative 22,000 people per year. And if you remember our definition of steady state, this is not steady state because it is changing over time.
Nice. So say you're a chemical engineer working in some plant, right? And you're given this problem to solve. They tell you 200 grams of one mixture is combined with 150 grams of another mixture to give you some total mass of a mixture that comes out with compositions of the elements in that mixture. we have a methanol water mixture where the first mixture that goes in is 40% methanol, so that means it's 60% water, and the second mixture that goes in is 70% water and hence 70% methanol and hence 30% water. And we're asked to find, alright, what's the percentage methanol and percentage water that comes out in the outlet stream, as well as the total mass of the outlet stream in this case. So how do we go about solving this? Mass balance. In must be equals to out, right? From our previous equation that we learned earlier on, there's no generation here, there's no consumption, there's no accumulation. We're literally just shoving things in and we're getting them out. So if we're to do a total mass balance on this entire thing, then we're left with the mass of stream 1 plus the mass of stream 2 should be equal to the mass of stream 3. Let's call this stream 1, call this stream 2, and call this stream 3, right? What goes in must come out. Simple. So that means mass of stream 3 is equal to 200 plus 150, which is exactly 350 grams. Sick. So now how do we go about calculating the compositions of each of these stuff now? So instead of doing an overall mass balance, let's be a bit more specific. Let's say we're just going to do a balance on methanol alone. What does that mean? We're going to look at how much methanol goes in and how much methanol comes out. And from that, we can back out the composition of methanol in the third stream. So if you do a methanol balance, this is the mass fraction or the percentage of ethanol times the first stream, percentage of ethanol in the first stream times the total mass of the first stream, plus the percentage or mass fraction of ethanol in the second stream times the total mass of the second stream. That's all the methanol that goes in, and the methanol that comes out is exactly the mass fraction of the third stream of methanol times the total mass of that third stream. So here we know that the mass fraction of methanol in the first stream is 0.4, that's 40%. So that's 0.4 times 200, plus in the second stream 70%, so that's 0.7 times 150. That should be equal to some mass fraction in the third stream that we don't know yet, that we're trying to find, but we know the total mass of the outlet stream or the third stream. That's, we just calculated it, 350. And now this is simple, one equation, one unknown. We can just solve this really quickly. If you plug this in the calculator, you get 185 is equal to 350 times x3. So that means x3, if you do your division and you shove that in a calculator, you get approximately 0.53, which is 53% methanol in the third stream. And now all we're missing now is the composition of water, but we can see here that the composition of water is just 1 minus the mass fraction of methanol rather, which makes sense. Everything needs to add up to 1 in the mass fraction. If you're looking at fractions or decimals, we're looking in percentages, everything must add up to 100%. So if we have 53% methanol, then that means mass fraction of water in the third stream should then be equal to 100% minus 53%. This is equal to exactly 47%. So that means mass fraction of water in the third stream is 0.47% or 0.47 or 47%. And that's it. That's the basic chemical engineering mass balance that chemical engineers use all over the place, and you just learned it in like 5 minutes, which is sick. So yeah.
Hey everybody, Quinn here. So earlier in the video we talked about a mixing tank and we solved a problem related to that. These are exactly the kind of problems you solve when you start out studying chemical engineering, but during your time as a chemical engineer you get exposed to so many more instruments used in a chemical process. Beyond mixing tanks, we have things like heat exchangers, pipes and pumps, turbines, reactors, compressors, splitters, distillation columns, and so many more. In chemical engineering lingo, these instruments are called unit operations, or unit ops for short. The name comes from the fact that each one of these instruments serves as one operation in a long string of operations that make up a process. So let's start by talking about a few of these in greater detail. Here's a chemical reactor. This is one of, if not the most important unit operation present in a chemical engineer's arsenal. These reactors are the tanks in which chemical reactions take place. In other words, this is the place where raw products transform into a final product under the right conditions. These chemical reactors have a lot of chemistry and physics that need to be taken into consideration. Will there be both liquid and gas in the tank? And if so, how will that affect the equilibrium of our final mixture? Will the tank maintain a constant temperature? If the temperature becomes too low or too hot, will it affect our reaction? And how fast will the reaction take place in this vessel? These are all the sort of questions that make up the study of reactor design, which is a course that chemical engineers usually take their senior year, and it's crucial towards basically every manufacturing process that a chemical engineer is involved with. Another interesting offshoot of reactors are bioreactors, and in these vessels, cells are used as sort of mini reactors that take in raw ingredients and turn them into useful products. So bioreactors are useful for making certain biological products like vinegar or sugar, but they're absolutely essential for the manufacturing of medicine. So for instance, the COVID-19 vaccine, most companies are pursuing some sort of vaccine based on exposing an individual to the characteristic spike protein that's on the COVID-19 surface. And, how are you going to manufacture enough spike protein to make vaccines for everyone around the world? Well, the answer lies in bioreactors, right? You're certainly not going to be doing this in a lab. You're going to need to do this on a large scale and take advantage of the capability that cells have. So as you can see, the accessibility of modern medicine relies on the work of chemical engineers, which is something we'll talk about in the upcoming weeks. So beyond reactors, we have things called distillation columns. Distillation columns are pretty easy to identify in a lot of chemical plants. In the footage shown here, you can see the massive columns popping out of the plant. And these columns are useful for separating two materials that are mixed together. So they take advantage of different boiling points of materials to heat them, turn them into gas, let the gas flow upwards, and then condense them again and repeat the process. Right, and the result of the procedure is to have a liquid phase at the top of the column that consists of the material of the lower boiling point, or the thing that more easily turns into a gas, and then have a liquid phase at the bottom of the distillation column that's entirely composed of the material with the higher boiling point, or the thing that's harder to turn into a gas. So if you slap two pipes on either end of this distillation column, then you've successfully separated the two materials, and you can use them in different places throughout your process. So where are these distillation columns used most commonly? Actually in the production of alcohol, right? That's right, you're not going to get any 190 proof alcohol without distilling the ethanol from an ethanol water mixture. In this case, ethanol has the lower boiling point, so it would be turned into a gas and pushed to the top of the distillation column. So we've talked a bunch about unit ops, but what happens when I put a bunch of these unit ops together into one process? Well, that's where the magic of chemical engineering comes in. With different kinds of unit operations, including mixers, reactors, separators, etc., we're able to produce a vast array of products on enormous scales based on raw ingredients found in nature. Chemical engineers can plan out their processes using something called a process flow diagram, or PFD, to see how these unit ops work together to make the desired result. Let's run through a few examples. So the example that you see here is actually a process for how gasoline is produced from crude oil. So while chemical engineers do great environmental work, the discipline actually started by pulling oil out of the ground and converting it to gasoline. And this was specifically important during the manufacturing of cars when they were invented. So all of these like hydrotreaters and catalytic reformers and alkylation units are all different kinds of reactors carrying out different chemical reactions. In this case, the jumble of hydrocarbons, or compounds containing hydrogen and carbon, that come out of the ground as crude oil are broken down, hydrogenated, heated and cooled, and reacted with other reactants to form things like asphalt, fuel oil, gasoline, sulfur, etc. You can see how chemical engineers have to deal with plenty of reactions, materials both in liquid and gas phases, and transfer different materials to different unit ops. And for something a bit timelier, we can look at a vaccine process flow diagram. This sort of model is exactly how the COVID-19 vaccine will be produced. A fermenter is a type of bioreactor in which cells express the desired product. The cells get harvested, filtered, and undergo a variety of separation techniques to get the desired product away from all that cellular jumble that we don't care about. And in this case, it would be the COVID-19 spike protein. The process ends in formulation, which is the stage where a biological product is prepared as a pill, a liquid, or a vaccine. In the end, these products are packaged and distributed to people around the world for use. As you can see, a basic understanding of material balances and unit operations and sort of the elementary stuff that we started off this video with lays the foundation for knowledge that can change the fate of society, whether it's by producing a new material, producing an old material more efficiently, or creating medicine on a large enough scale to end a global pandemic.